This is the second part of the video on inverse trig functions. So we're going to try a few examples of working with inverse trig functions on restricted domains. So the note here says that if you take the inverse sine of sine, you'll get theta in some cases, and that happens when the angle that you're working with is in the restricted domain. Otherwise, you're going to have to find one that does fit those restrictions. So just as sort of a reminder, inverse sine is restricted negative pi over 2 pi over 2. Inverse cosine is restricted 0 to pi, and inverse tangent is the same as inverse sine except without the endpoints. Okay, so for the first one, that's easy, right? Notice pi over 3 is already on the restricted domain between negative pi over 2 and pi over 2. So you take the inverse sine of the sine of pi over 3, and out comes pi over 3. Oh, if they were all that easy. Look at the second one. The second one says find the inverse sine of the sine of 2 pi over 3. So the 2 pi over 3 is outside of that restricted domain, right? It's over here somewhere. There's your 2 pi over 3. Well, sine we said was between negative pi over 2 and pi over 2, so I'm looking for something on the right half. What if I reflected it over the line here? What's over there? What's over there with the same y value? Remember, sine is the y value. So what's over there with the same y value is pi over 3. I could have also gone back to my old-fashioned unit circle, right? Go back to your unit circle and look for the sine of 2 pi over 3. The sine of 2 pi over 3 is over here, square root of 3 over 2. What's the inverse sine of square root of 3 over 2? If you said, give me a y value of square root of 3 over 2, the only place it could happen is up here at pi over 3. So you could turn those into numerical values and then work backwards too is another option. All right, inverse sine of the sine of negative pi over 4, problem's done. Negative pi over 4 is on that restricted domain, so we just get negative pi over 4. Right, inverse cosine of the cosine of 5 pi over 3, well, 5 pi over 3 is where? It's down here. So it's a negative cosine value, but cosine is on the restricted domain from 0 to pi. So it's got to be something that has a positive value for the cosine, right? Because we're to the right of the axis here. But is between 0 and pi. So go straight up. What's up on the top here that matches up with 5 pi over 3 is got to be pi over 3. Again, we could do with the unit circle also. Cosine of 5 pi over 3 is positive 1/2. Go up to the top. Where's my positive 1/2? It's at pi over 3. Inverse cosine of the cosine of pi over 2, we're fine. It's just pi over 2. Inverse tan of the tan of 3 pi over 4. Well, 3 pi over 4 is outside of the restricted domain, right? It stops at pi over 2. So the tan of 3 pi over 4 I know is negative 1. Because we're in the second quadrant, sine and cosine are the same at that point, except that the cosine is negative and the sine's positive. So where else is the tan value negative 1? Between negative pi over 2 and pi over 2? Has to be down here. Fourth quadrant, negative pi over 4. All right, so that's how we do those. If it's not already on the restricted domain, then you've got to look to find what a corresponding angle is with that same trig function, but on the restricted domain. All right, what about something like this? Suppose you want to find the tan of the inverse sine of 12 over 13. Oh. So you notice in my directions I said find by drawing a triangle. The other ones we all did were like sine of the inverse sine or cosine of the inverse cosine. Well, this is tangent of the inverse sine. This thing over here is an angle. It's an angle where the opposite and hypotenuse have a ratio of 12 to 13. So let's draw ourselves a right triangle. Pick a spot for the angle. I'll pick the angle over here. Don't pick over there because that's where the right angle goes. Sine is opposite over hypotenuse, so opposite hypotenuse. Now I got to find the third side. So I happen to know that this is a 5, 12, 13 triangle. If you didn't know that, you'd say a squared plus 12 squared equals 13 squared. 12 squared is 144. 13 squared is 169. So subtract them, you get 25. Square root, you get 5. I'm going to need that third side, that 5, because now I want to find the tan of that angle. Tangent is opposite over adjacent, so the opposite side is 12, the adjacent side is 5. So it's important in this case to recognize that that inverse sine of 12 over 13 is an angle measure. You're trying to find the tangent of an angle. That's the tangent of the angle. Those are all my instructions. All right, let's try these. Sine of the inverse tangent of 7/24. So again, we'll draw ourselves a right triangle. Tangent is opposite over adjacent. Opposite, adjacent. Again, this thing here represents an angle. You're going to need to use the Pythagorean theorem to find the third side. The third side is 25. Maybe it's worth mentioning all of the Pythagorean triples, because there are Pythagorean triples that can save you a lot of time. Like if you get the two legs of 7 and 24, you notice that I've just been going back and saying, oh, well, of course the third one's 25. But what are a list of those Pythagorean triples? In other words, sets of numbers that are guaranteed to always give you a right triangle. Three, 4, 5, right? 3 squared plus 4 squared gives you 5 squared. 5, 12, 13 always gives you a right triangle. 7, 24, 25 always gives you a right triangle. 8, 15, 17 gives you a right triangle. 9, 40, 41 gives you a right triangle. And by the way, any multiples of these also. So if 3, 4, 5 works, so does 6, 8, 10. So does 9, 12, 15. In the second one, 5, 12, 13 works, so does 10, 24, 26. Right? If they're trig ratios, they'll usually be simplified down to lowest form, but anytime you see like a 7 and a 24 as the two legs of a triangle, you can automatically put the 25 there without having to show the Pythagorean theorem, and it speeds it up a little bit for you too. All right, look at the next one. The next one says the cotan of the inverse sine of 5/13. So pick a theta. Sine is opposite over hypotenuse, so opposite hypotenuse. Oh, look at that. The hypotenuse is 13, one side is 5. Boom, the other side's 12. 5, 12, 13 triangle. I want the cotan. Well, if tangent is opposite over adjacent, then cotan is adjacent over opposite. 12/5. All right, let's take a look at the third one. This one is a little bit different because look at this. This is the inverse sine of negative 4/5. So sine is opposite over hypotenuse. So there's my opposite. There's my hypotenuse. Well, hypotenuse is always positive. So the opposite side is the one that's got to be negative. So I got two options. One is I can draw my triangle like this with the opposite side negative. Hypotenuse is positive. But where's the inverse sine? The inverse sine exists in quadrants 1 and 4. So really, I've got to draw it this way so that I'm in the fourth quadrant. So there's my angle measure. The opposite is negative 4. The hypotenuse is 5. Oh, look, a 3, 4, 5 triangle. There's my 3. Okay. Now I can take the cosine as adjacent over hypotenuse, and I get 3/5. So using those restricted values for inverse sine is important here, is I got to know which quadrant I'm in. I'm in this fourth quadrant. Cosine's 3/5. All right. For number 4, cosine of the inverse tangent. If you've seen enough of these, you want to fast forward through, that's fine. The couple here don't have nice Pythagorean triples like the other ones did, so you're going to have to do a little bit of work to get to the missing side. Not terrible, though. Tangent is opposite over adjacent. It's positive, so I'm going to go with the first quadrant. Here's my theta. Tangent is opposite over adjacent. And so the third side is 4 squared plus square root of 2 squared. 16 plus 2 is 18. So the square root of 18 simplifies to, what, 9 and 2? So 3 square root of 2. Now take the cosine of that angle. The cosine is adjacent over hypotenuse. Hit top and bottom with a square root of 2. And I get 4 square root of 2 over 3 times 2 is 6. And that simplifies to 2 square root of 2 over 3. All right, for number 5. I'm looking again at an inverse sine of a negative. So the inverse sine of negative 1/2 is going to put me again in that fourth quadrant, because remember, sine works from negative pi over 2 to pi over 2. So sine is opposite over hypotenuse, so opposite over hypotenuse. And then I need that third side, so a squared plus 1 squared equals 2 squared, square root of 3. And now secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, then the reciprocal is hypotenuse over adjacent. Hit top and bottom with a square root of 3, and I get 2 square root of 3 over 3. All right, for number 6, the sine of the inverse cosine of 3/7, first quadrant, so everything's positive, opposite, adjacent over hypotenuse. Find the opposite, that gives me 49 minus 9. Take the square root. Simplifies to 2 square root of 10. And now you can take the sine. So sine is opposite over hypotenuse, so opposite over hypotenuse. All right, every once in a while you'll have one to simplify that's not in terms of numbers like we had, but rather in terms of x. So for these problems, we assume that x is positive and defined for the given problem. So we're not, in the first one I'm going to give you, x is not an issue, but it could be that I give you like an inverse tan of something, and if it were pi over 2, it would be bad news, so we assume that it's not. So how do I do these? Well, let's start with a right triangle. Pick a spot for theta, pick a right angle. So remember again that this thing over here is an angle. Is an angle whose cosine is equal to x, or we can even think of it as x over 1. So if cosine is adjacent over hypotenuse, what's the third side? Well, if a squared plus x squared equals 1 squared, I'm going to call this a for just a second, then a squared equals 1 minus x squared if I subtract an x squared from both sides. And so now take the square root of both sides. This piece over here is the square root of 1 minus x squared. Try the Pythagorean theorem. You'll get 1 minus x squared plus x squared equals 1. So now I need to find the sine of that angle. So the sine of that angle equals opposite over hypotenuse, which we can just write as the square root of 1 minus x squared. Right, and so that's how we do it if there's no numbers. We could write this whole thing in terms of variables. We don't need numbers. So draw yourself a right triangle, organize and label things, and then once you have the 3 sides labeled, then just use right triangle trig to find the missing trig ratio. All right, these are just the instructions. All right, let's try a couple more and we'll be done. For the first one, the sine of the inverse tangent of x. Again, we're saying over here, that's theta. So the tangent of theta equals x over 1. Mark my theta. Tangent is opposite over adjacent. How do I find the hypotenuse? C squared equals 1 squared plus x squared. So square root of both sides. Don't try to separate the radicals on the right side. I'll get c equals the square root of 1 plus x squared. So this hypotenuse here is the square root of 1 plus x squared. Sine is opposite over hypotenuse, so it's opposite over hypotenuse. I am going to leave it like that, unrationalized in the denominator. All right, let's try this last one. The sine of the inverse cosine of 2x. Well, it's different having a 2x than an x, but it's probably not terribly shocking. Again, this thing over here is your theta. Another way of saying it is that the cosine of that angle is 2x over 1. Cosine is adjacent over hypotenuse. So that's the adjacent leg. That's the hypotenuse. We want to find this third side here. So a squared plus b squared equals c squared. Remember when you square a 2x, you square the 2 and square the x, so you get a 4x squared. Subtract that 4x squared from both sides, and then take the square root. And again, you can't split that radical, as tempting as it looks. So you get the square root of 1 minus 4x squared. So this piece over here, square root of 1 minus 4x squared. So now sine is opposite over hypotenuse. Well, the opposite side is the square root of 1 minus 4x squared. The hypotenuse is just 1, so I'm not going to write divided by 1. There's my answer. And that's the end.